Hello, welcome back again. This time we're going to focus on just the BJT transistors. Just kind of the joke from the the slide. BJT, the T actually does stand for transistor. I'm not worried about it. People say BJT all the time. It's redundant. It's like saying pin number. But people do it. I'll do it too. So don't even worry about it. So BJT transistors, they are current controlled. That is the most important thing to know about them. So you would turn it on, let's say just for example, you would turn it on with 5 milliamps, and you might turn it off with 0 milliamps. You're going to always turn it off with 0 milliamps, but the amount that's needed to turn it on depends on how much current you need to flow through the other side. So the way this thing works is you're going to always ground the emitter, you're going to have your load connected to some positive voltage source, and depending on how much current your load needs, like let's say it needs 100 milliamps, then you're going to transition it with 1/10 of that, right? So the on value is going to always be 1/10 of what your load needs. So you have to figure out what the load needs first, then you can size the rest. I'm getting ahead of myself a little bit. But these things are cheap, which is why they're extremely popular. The ones that we have, you can literally get for like 1 cent. Less than that. They're really cheap. They do have the problem that you won't like, that they require careful resistor sizing. So when you use it, you have to size a resistor just right to get that current where you want it. Because the PIC is going to always give you 5 volts for on and 0 volts for off. So you have to size a resistor to get that on-off current just where it needs to be. Let's just go ahead and draw on a full example. So your load can be whatever you want. Just for this demonstration, let's say we're doing an LED. LEDs, if you're only doing one of them, you could do it straight off the PIC. But let's say you're doing like 15, right? So you would have the microcontroller here. You would have some control line. It would have to go to the base. The LEDs that we use require 10 milliamps. Assuming that you've got a 330 ohm here and a 5 volt source that says 330, just take my word for it. So you have to then size this resistor as appropriate. So when it's at 0 volts, that's easy. You get 0 amps because it's ground to ground. That part was easy. When it's 5 volts, you want to be at about 1 milliamp. So you can do the math. It's not that hard. It turns out for this example to be 5K. So this resistor needs to be 5K. 5K isn't a real resistor size, so we could actually do better and pick a real size. A real size, you could look at your notes from the first day. I think a 4.7K would be a real resistor size. I get those numbers confused, but I think 4.7 was one of the ones you could really use. So the answer to this problem is 4.7K. That's how you have to size your resistor. I skipped ahead of this, but I kind of wanted to also mention, if you're a double E, you probably have heard that there are these diode drops in this thing. The base to the emitter has a 0.7, then the collector to emitter has like a 0.2. Ignore it. So they don't exist for this class. So for any homework you do, any exam problems you do, those diode drops, they don't exist. The current ratio we mentioned a couple times, 1/10 is the only thing you need to know. Technically, there's more to the story, but 1/10 is a nice way to try to get a nice digital transition. That should be well below what most transistors can do. They can do at least a 1/10 gain, and that 1/10 will put you into a nice clean digital region. So it'll just be on or off, and there is no in between as far as we are concerned. One more. So let's say we were doing, instead of an LED, we were doing a motor. So if in this example, I don't know, let's say it was, I'll pick something silly, a 24 volts up here, but then this motor was a 240 ohm motor. Tried to pick numbers that would make my math easy. Then I would figure up how much current this thing needs. So with a V equals IR, it looks like it'd be 224 divided by 240. So this thing would be 100 milliamps. And if you wanted to actually control it from a microcontroller, oops, forgot my resistor there, at 5 volts, you just have to do the game again, V equals IR. 5 volts, this thing needs 10 milliamps to control it. So our R here is equal to 5 divided by 0.01. So our R in this case looks like 500. And of course, to pick a real one, we would need 470 ohms there. So hopefully you get the idea on this. The math is not hard. It's dividing by 10, all right, and some V equals IR. So go ahead and take a minute, see if you can do this example. A couple different options, see if you can figure out what it is. So hopefully you understand the math. I think you get like 166 when this thing is done. You could, when you pick a real resistor size, take that up to a 220. That would be fine. I would count that right. Or I think a little closer, there's a 150 option. So the answer that I would consider as the best answer to this question is 150 ohms for your input resistor. I could go through the math, but hopefully you've got it worked out. I don't think I need to show it again. I just wanted you to practice. As far as real devices go, we're actually going to use these in lab. The one that we're going to use in lab, it's called 3904. So you'll actually see the number 3904 written on these things. It's really small. The main thing you need to know about these is which legs are which. There's a link on courseware to the data sheet, which I think is the next slide here. But I'll just tell you what they are. They're pretty easy. Leg number 1 is the emitter. So leg number 1, you will always just ground with these. Leg number 2 is the base. So it's going to be the one that goes to your microcontroller. And then leg number 3 is the collector. It's the one that's going to be connected to your load. And just to kind of mention it again, make sure your load always has power up here. The way these guys work is there's no power anywhere in this chip, right? So power has to come from somewhere else. The idea that these guys do is they either connect you to the emitter, so like they either connect you to ground to give you a path, or they leave you floating. So it means no current will go through. So that's how they kind of break the circuit, right, to turn things off. But power has to come from the other side of your load. There's the link to the data sheets. Hopefully you know where all our data sheets are at in the course. I do want to tell you just a little bit more information. 99% of the time we're going to be using the 3904, which is what's called an NPN transistor. Stands for negative, positive, negative. These work the way I've described so far, right? They have a ground on the emitter. They have, a resistor going to a microcontroller. They've got the load. There is another type, which probably 1% of you will use in your projects. They are called a PNP. Just to share how they work, they're similar in that a microcontroller goes to the base, but they're different in that, well, the emitter's on top. You probably saw that right off. Then the collector is on the bottom, and here the load is going to get connected to ground. So they work in pretty much the same way. They have the same constraint in that when current flows here, then it allows current to flow there. So same concept. Only thing that's tricky is in order to allow a current to flow in this part, you have to hold the microcontroller at 0 volts. So they turn on when it's at 0, which messes up some people. You could go ahead and do an example here. I don't want to go through a full example. It works just like it did before, right? So, I mean, if we just kind of draw on a couple pieces, so I'll just go ahead and put this at 5 volts. Let's just say we were to do our good old LED. So our LED needs 10 milliamps. So in order to control this thing, we want to control it with 1 milliamp, and the resistor there should be something near 5, so 4.7. So pretty simple concept, and you would turn it on with 0 volts. So that's kind of all you need to know about transistors, BJT transistors. Come back next time, we'll tell you about MOSFETs.